Hi, everybody. So today we're working through more friction problems. This is friction part two. We'll start with normal force. Okay, so in which picture is the girl subject to a larger normal force? Well, we can see that in the first picture, this is a boy pushing a girl on a sled. And we all know that if you're significantly taller than the person sitting, it's kind of hard to push completely horizontally. You're pushing down a little bit. Then in the next picture in letter B, he is pulling up on a rope, where obviously you can't pull horizontally, then you'd be pulling on the ground. So there's always angles involved in these kind of scenarios. In which picture is the girl subject to a larger normal force? Well, let's draw a free body diagram real quick of the girl. Okay. Got girl in scenario A, and she has her own mg. Then we have these two components, right? We've got this push force that is pushing 30 degrees below the horizontal. Well, cosine of that 30 degrees, right, would be this adjacent section here. That would be the x, and then the sine would be the y. So we could say that this is f cosine theta, and this would be f sine theta. Then the normal force, right? Normal force in this scenario, let's say normal force A, that needs to equal mg and f sine theta. Now on scenario B for the girl, right? She's got her mg, then that pull force is going to the right and it's going up. So again, here we have x would be cosine, y would be sine to that angle. So we have f cosine theta and f sine theta, then normal force. Okay. Well, that normal force, right, that needs to balance this now. This is going to be a little bit more complicated. With this summation of forces in the y for part B, normal force plus f sine theta minus mg will equal 0. That means that your normal force will be mg minus your f sine theta, whereas in the other scenario, it was mg plus f sine theta. So therefore, when you're pushing down, the ground must compensate, right, to give you a stronger normal force. So in which picture is the girl subject to a larger normal force? That would be part A. Now on number 2, in which picture does the girl feel more kinetic frictional force? Remember, kinetic frictional force is the kinetic friction coefficient times the normal force. Since it seems to be the same sled on snow, we assume that the friction coefficient is going to stay the same. So the only thing changing here is the normal force. And if you have a stronger normal force in part A than part B, then in part A, do you also have a stronger kinetic frictional force? Stronger the normal force, stronger the friction. Now, assuming F equals F in both pictures, saying that the force is the same throughout, which force produces more acceleration? So we'll do summation of forces in the x direction to find that acceleration. So we now have a frictional force in the x direction. Kinetic friction, let's get that better. Kinetic friction going left. Now, summation of forces in the x for part A, we have f cosine theta minus friction of k equals ma. So then we have f cosine theta minus friction k divided by m equals a. And then let's look at the summation of forces in the x for part B. So summation of forces in the x for part B, we again have f cosine theta minus kinetic friction equals, oops, oh goodness, equals ma. So we're going to get something very similar. Acceleration is, again, F cosine minus friction K divided by M. So the equation is going to come out to be the same, assuming the F is constant, also assuming that the M is constant. It is the same person. The only thing that's different here is the friction, and the friction is stronger on part A than it is in part B. So that means that you have a stronger negative force in part A that gives you a stronger acceleration in part B. So part B, that force would produce a greater acceleration. Okay, now for our next problem, a pulley with symbols. Whoa, there we go. Pulley with symbols. Now, mass M on a rough horizontal surface is connected to a ball of mass M1 by a lightweight cord over a lightweight frictionless pulley. A force of magnitude F at the angle theta is applied as shown. Determine the acceleration of the two objects. So what we can do here, we're going to do what's called melting the axis. We're going to assume, since the direction of motion is in the same direction for both objects and the acceleration is the same, we will actually call that positive for both free body diagrams. So we will start with FBDs. So let's just do this down here. We've got M1 down, it has M1G. Up, we have a tension force. And that's it. It has no contact force at all. Then M2, it is on a rough surface, right? So it has down M2G. Up, it has a normal force. It has that same tension force pulling back on it. And then it has this F force at some angle theta. Now, let's break these down because we need to find the acceleration. So break these down into their x and y summation of forces. So summation of forces in the x for 1 is 0, nothing going on there. Summation of forces in the y for 1, we have the tension minus M1G equals M1A, right? Then over here, we have two summation of forces. Let's do the y first. We have normal force minus, we also have normal plus F, that will be the sine, the opposite of that angle, F sine theta, minus M2G equals M2, worried that was going to happen, equals M2A. Okay. Now let's do the x. Summation of forces in the x for 2. We are going to have F cosine theta pulling us along, and we are going to be resisted by tension, and that would equal M2A. In the y, that equals 0, right? That was my bad. That equals 0. In the x, we get M2A. All right. Now we need to find the acceleration. So first, I forgot something. Oh, I forgot the friction. That's what it was. Goodness. All over the place today. All right, so we have a negative friction force in the x. So let's move you over. Minus kinetic friction. Okay. Now we need to analyze the tension and the friction. Let's do the friction first. We've got Fk, okay, that will equal mu sub k times normal, but we can see what the normal force equals, right? So normal force up here on the summation of forces in the y direction, if we solve that for normal, we would get m2g minus f sine theta. If we added m2g and subtracted f sine theta to the other side, we could solve for it that way. So that will be our Fk, and that all equals m2a. Now, what we'll do is we will stack and rack. So this is something that we can do with a summation of forces if the direction of motion is all in the same melted axis, right? So let's look up here. The direction of motion for A, okay, the acceleration is along that length. Then this pulley melts the axis, and now the acceleration is all along that direction. So since the acceleration is constant along this, what we can call a melted axis, then we can actually combine those summation of forces. So let's do exactly that. Because the acceleration is going to be the same, right? So we have T minus m1g equals m1a. Then we will add the other forces. We have F cosine theta from right here minus tension minus the friction that we have right here, mu k times quantity m2g minus f sine theta. That would equal m2a. So we will add all of this together. The tensions, as you can see, will cancel. So what we will end up with is f cosine theta minus m1g minus mu k times the quantity m2g minus f sine theta, all equals m1a plus m2a. Now, when you get to this section right here, right, you can factor out that a to get m1 plus m2 times quantity a. That is a little bit cleaner, and that is what I prefer to use in these summation of forces situations. So that's what I'm going to substitute there. Now we need to determine acceleration. So what we'll do is we will divide, which I am going to cheat here just to circle that right there. Oh, I lost my parenthesis. So we will divide all of that by the summation of masses, and voila, we have our acceleration. Now, this problem is titled Pulleys with Symbols. The reason it is titled that is because you will be solving a lot of problems in AP Physics using just symbols. They will sometimes give you one or two numbers, but when it all comes down to it, you just have a bunch of variables. Now, this is the exact same situation. You just have a bunch of variables in this answer, but that is what we have to settle for this problem. And it's best to keep this down to as few variables as possible. So if you can see, the only variables we have are F, M1, M2, G, and the theta. Okay. There is the force pulling on it, the masses, can't forget gravity, and there is a theta involved. That's all we have. So we were able to get rid of tension. Tension is a common force that you can just get rid of, usually through this stack and rack method up here, or you can solve for tension in one equation and substitute it into the other, which is what I recommend doing for most of your problems if they have a tension involved. All right, last one we have is frictional misconceptions. So we have this force P pushing upward at an angle theta relative to the horizontal on a block that seems to have this wall that has friction on it, right? Now, let's draw the forces on the block in a free body diagram. So let's do that right here. We have this block, and then we have mg. We have this force pushing up, a pushing force P. Now, that theta is in a tricky spot. So we will say that it is pushing up. Okay, there is our triangle. So it is pushing up with P, and we have to look relative to that theta. That would be sine, opposite for y. So P sine theta going up. Then we are pushing to the right, P cosine theta. Okay. Now, we also have a normal force that is going to keep that block from melting right into the wall, right? So now everything seems nice and balanced. But we have this rough wall, right? This wall has a rough surface. We can see that from the image here. Those bumps notate a rough surface. Now, which way do we make the friction, though? That depends on where the block is about to move. So, which way is the friction directed if the block is about to slide up due to force P? Okay, let's say that push force is about to push it upward, right? That means that for block A, the friction would oppose motion, giving us a downward static friction if it is about to go up. And it's all about where the motion is going for kinetic, or where the object is about to go or has the potential to go for static. Now for scenario B, the block is about to slide down due to force W, due to the weight. Well, that means it has the potential to fall, and force P is really just barely keeping it there. That means that the friction would be facing up. So depending on where the block is about to go, that friction can actually change directions. Now also remember that static friction is going to match whatever force is being put on it until it reaches that maximum static friction. It can give a weaker force if it needs to, but once you break it and it starts moving, it's all kinetic friction from there. Now, number 3, a crate is sitting in the center of a flatbed truck. The truck accelerates to the right, and the crate moves with it without sliding. What is the direction of the frictional force exerted by the truck on the crate? Now, let's do this down below. So we have a truck with a crate. We'll call that C. Okay. It's got its own mg. It's got normal force. And the truck is going to the right. Now, what is the direction of the frictional force? Well, we know that in the problem it says the crate moves with the truck without sliding. So one common belief is that we would just put a truck force, right? The truck is somehow moving it, and then the friction is going to oppose the motion, right? But that's not true. The only thing acting on this block is friction. So there is no mysterious truck force. The force that the truck is using to move the block is static friction. The static friction allows that block, that crate, to cling to the flatbed truck, right? It wants to stay right there with the flatbed truck. So as it accelerates, that static friction is going to allow it to keep going until there is a break in that force, right? So the static friction is actually going to pull it along with it. All right, so this is the end of friction part 2.